We are honored to have our guest host Mishli with the IP products from Unbound Tech. So please come to the stage.
Okay, thank you. Hi everyone. It's a pleasure meeting you. So hope you can hear me well. Hope you had a good lunch. And happy to present you today a bit about multi-party computation. And now we apply it for key management, key protection. So before I start, just wondering if you could please raise your hand, anyone in the audience who is familiar with multi-party computation. Just wondering. Nice, okay. So it's not the majority yet, but it seems like we keep asking these questions for the past few years, and it seems like the number of hands is actually rising from event to event, so it's good that it's making traction. Okay, so let's get started, right? So, of course, let's start with some context, right? We know that cryptography is central tool of computer security. I don't need to mention it to this audience. It all relies on secrets, right? So be it signing in PKI, be it encryption, key exchange, and obviously authentication. Now, the threat model is rather simple, right? If the secret is stolen, game over, right? All security is lost. You can decrypt anything that was encrypted with the key. All the signing protections are lost. Users can be impersonated. And lastly, you don't always think about it, but if cryptography is compromised, this is actually the easiest and most efficient attack, right? Because you are actually using the allowed known APIs, and you go completely undetected under the radar. So obviously, that's a very bad issue to have a key compromised. Now, in modern environments, this is actually becoming a bigger challenge, right? So first of all, we have much more keys than we used to have in the past. There are many new applications, and the amount of machines, devices, connected devices is rising exponentially, right? So the number of keys is very, very big, but in addition to that, there's no perimeter anymore, right? So if you could say that most of the key management and key protection technologies we're using today were actually designed and developed for an on-premise perimeter-based environment. Okay, that's the reality of it. And now when we are very fastly transitioning to a no-perimeter environment in the cloud where keys are not in our hands anymore, right? It's in the end devices of end users or customers or employees, or it could be in the cloud, held by a cloud service provider, right? So this model is very, very challenging to get the guarantees that we used to have on key protection and key management. And there are, speaking generally, there are a few solutions available today. And before getting to secure multi-party computation, which is the topic of our talk, I'll review some of the existing solutions out there for key protection and key management. Okay, so obviously, that's dedicated hardware, so HSMs on the server side, smart cards, tokens, even TPM inside some of the endpoints. This is the traditional method of key protection. It provides clear guarantee of security, right? You know that the keys always stay inside the secure environment. The processing is within the hardware. There is strong physical protection, so you wouldn't be able to access the key material. And if you did get access, it will zero it, etc. And it doesn't run any other code, only the cryptographic code. And obviously, it's certified, right? So FIPS, common criteria, etc. And obviously, the administrative controls are very tight. Some of them require tokens in order to access HSMs, etc. So this is kind of the gold standard. It's trusted. It's field proven for decades already. So that's kind of the way to go for many of the high security deployments, PKI, encryption, etc. It does have some operational challenges that get manifested when we actually transition to a perimeterless environment, right? So scaling or modifying an environment to scale is very challenging, right? There are some difficulties in interoperability if you have solutions from different vendors, unfortunately. And if you're looking at the endpoint side, right, end users and employees have significant pain with dedicated hardware devices they need to carry, they need to remember and not to lose them, right? That's kind of a hassle, both from the user experience side for the user and from the management perspective to the enterprise. Cloud HSMs indeed is the deployment in a way, but they still have an issue with the ownership, right? So you could say it's partially technical issue, partially psychological issue, right? It's not exactly the same as having it on premise and controlling it. But really the key downside of the hardware, at least to our point of view, is the agility, right? So the ability to carry out updates to the deployed hardware is pretty low, right? Updates are expensive, they're lengthy, they mostly will require downtime, and when a vulnerability is discovered, the consequences on the security model, on the security of your system could be very significant, right? This is an example of few vulnerabilities. One of them is about ROCA, which was, I think, disclosed in 2017, and another one is older, PKCC11 bug from an earlier time. But just recently, you know, in June, a major HSM breach was disclosed, and it was published by Ledger in Black Hat 2019. And essentially, you know, the bottom line, there's a lot has been written about it, so I wouldn't repeat all of that, but the bottom line is that the hackers were actually able to upload arbitrary unsigned firmware into the HSM, right? And this firmware, they use this firmware to actually remotely extract all the keys from the HSM. And since the firmware has been replaced, essentially, an HSM that was compromised cannot be patched, right? I mean, you can patch it, right? But you will never know if the patch was applied or not, because the firmware that is, the malicious firmware on the device would never essentially let you know whether you really installed the new firmware or not, right? It can, of course, manipulate the process. Now, I think the major takeaway here is not about the vulnerability, the specific vulnerability itself, and not about the vendor itself. It doesn't really matter. I think there is a more fundamental fact we should all remember, right? All software, all vendors will have vulnerabilities. Bugs is a fact of life. I'm sorry. It could be in vendor code. It could be in the third-party libraries that you use in the operating system. And you know, it's not really going to change, unfortunately. I mean, the development processes get better. There is better auditing, right? But the systems are increasingly more complex. And obviously, the fraudsters, you know, they are also becoming much more sophisticated. So in such kind of a landscape, you would actually want to ask yourself, what am I doing to recover when a hardware vulnerability is discovered, right? If you look at the 2019 attack as an example, the compromised hardware must be replaced. You can't even trust it, right? And you're not always sure if it was, you know, a compromise or not. So this raises a very clear question mark on, you know, this issue of the ability of updating promptly when an issue like that takes place. Now I'm switching to another approach of using a pure software for protecting keys, right? This would be mostly methods based on white box cryptography. And essentially, it has a lot of benefits on the operational side. Very easy to deploy, fast to scale. It's easy to fix vulnerabilities and to update because it's all software. Easy to incorporate new algorithms. And obviously, it's kind of platform agnostic. But on the security side, there is an issue because it's kind of a cat and mouse game, right? This is a model that doesn't provide a clear security guarantees. So for example, when supplying such an algorithm, you cannot assert the level of the security that it will provide you or any kind of guarantees. As an example, there was a Chess 2017 captured the flag context. And there they had researchers and developers that are actually invited to submit their white box crypto implementations and to break break these challenges. So there have been roughly 90 challenges submitted, and absolute majority of them were actually broken in the first day. And the two winners, the winner, I think it was like 28 days, and the runner-up was like, 10 or 14 days, right? So essentially, it's kind of, again, a cat and mouse without a clear guarantee of security, right? Which is what we are looking when we protect such sensitive assets. Another emerging approach for protecting keys and sensitive secrets is trusted execution environments. So obviously, I guess many of you are familiar with Intel SGX, ARM Trust Zone, etc. So this is indeed a nice model that provides protection for any kind of data that you process within the TE, the Trusted Execution Environment. It will encrypt the memory. You wouldn't even be able to view the code that's running in the enclave. It's essentially blocked and obscure to all code running outside in the rich execution environment. And you even have attestation methods to ensure that you run and execute the correct code, right? So on the theory side, it looks like a good solution and flexible solution for that. However, there is an issue here, right? So the fact that you don't really have full isolation and you actually run on the same CPU and dedicated crypto code and general purpose code at the same time, this creates a landscape that could enable software side channel attacks. Okay, this is a class of attacks that can be carried out remotely. You actually don't need any physical access. And essentially, they can be in the hypervisor level or in the machine level. And the bad thing about side channel attacks is that it puts you again in this cat and mouse situation. Okay, so you can defend against the side channel attacks that you know, but it's really, really hard to defend against attacks that you don't really know yet. And I think that we all seen a pretty good example in the publications of the attacks of SGX, where you see attacks continually being published after the previous ones have been patched. In terms of deployment support, so it's beginning to make more ways into the cloud. It's not really clear yet whether the deployment will be cloud agnostic or you'll have it, varies between specific vendors. But it has some more ways in order to be, a globally adopted solution in the cloud in a standard manner. So now let's start talking about MPC, right? That's the reason why I'm here today. So secure multiparty computation is essentially a well-researched subfield of cryptography. It's actually in the academia since the late 80s with thousands of research papers. And it was pretty much theoretical until around 2011. And now it's actually making its ways to production, to massive industrial use cases, and we'll talk about it later, of course. And it's also a very active applied area of research today due to that. And the basic idea of MPC is actually very exciting. It sounds a bit like magic when you hear about it for the first time. It's the ability to compute on private data without revealing the data, right? So imagine that you could essentially have several parties compute a function without ever revealing the inputs to their function, but being able to see the result. Okay, now the security models are well defined, and all the security guarantees that we'll talk about are proven mathematically, right? Every protocol comes with a full proof of security that is mathematical. And let's see, an example. This is a toy example, of course, but just to kind of get everyone to see the concept. Let's assume that we call it the dining cryptographers problem, right? You have a group of cryptographers that want to go to lunch, and they want the person that has the highest salary to buy lunch for everyone, but they don't want to reveal each other's salaries, okay? Nobody wants to know or to tell how much they get paid, right? So essentially, what they're doing, these cryptographers, so Bob, Alice, and Eve, they're essentially executing a multi-party computation protocol between them. right? It's in a communication protocol. And essentially, this protocol is able to output the result, but still keeping everyone's salary secret, okay? And I just want to stress, there is no additional party involved. It's only these 3 people, okay? There is no one else. There is no trusted party they can all share the secrets with. So essentially, all the communication is internal to this group. Okay, so that's essentially that's a toy example, but a useful demonstration to what MPC can do. Now, also important to mention, it's very generic, right? So the tier of MPC applies to any function and to any number of parties, right? So it has a lot of power, but the downside is performance and security, right? You need to be very, very skilled in order to create an implementation that is efficient and secure, right? It's a field for experts nowadays. The knowledge is not that widespread today. Here's some more advanced example of an MPC use case. That's actually a privacy-preserving use case. So this is about DNA comparison, right? So here, essentially, the function is to compare DNA of 2 people, or to compare one person's DNA with a database, right? Essentially, without revealing the data itself, but just getting the result. Okay, so this is another area where MPC is being used. And today, essentially, most of the areas where you will meet MPC is in areas where you need to preserve privacy. Now, Unbound has taken a pretty different approach. We're actually not applying MPC for privacy, like most other applications. We're applying it for security. Okay, so essentially, if you think about how you secure keys today, you operate in a kind of a centralized trust model. Okay, you take your most sensitive keys, you put them inside the HSM, right? You put a moat around the HSM, you put it in a very secure location, and essentially, this is kind of a single point of compromise, but you protect it very, very strongly, and you have all the clients that want to consume cryptography accessing that, right? That's the typical way of how the trust model works today. Now, essentially, we are now changing this trust model to a distributed trust model. Okay, essentially, this key that has been in one place, one location, is now split. Okay, split into random shares, right? And some of you might ask, but wait, that's, Shamir's secret sharing is actually doing the same, right? You can actually split the secret into multiple shares. But here, there is a new aspect. The new aspect here is that these shares are never united throughout their life cycle, okay? So essentially, all the key operations, including signing, including generation, including decryption, encryption, essentially take place without ever combining these key shares together to the full key, right? So essentially, you could say that we eliminated the private key, okay? The private key doesn't really exist anymore in itself as an entity on a single machine. So you never need to trust anymore a single device, a single machine with your keys, right? Because the keys will never be in a single place. And it's a pure software model, right? It's working on kind of any hardware, any platform. So in a bit more detail on how it works, and here I kind of use the 2-party example because it's easier to explain. Okay, the private key essentially exists as 2 separate, completely random shares. Okay, each of these shares essentially contains no information about the key material. Alone, they have no value, right? It's like kind of public information. You can't do anything with that. They are stored in separate locations. We'll talk about it momentarily. And essentially, these key shares are never combined at any point in time, okay? When we do signing, when we do encryption, decryption, when they are generated, they're never combined in the same place. And essentially, throughout the key lifecycle, there is no full key anywhere, not in the memory, not in the disk, and not over the wire. And in addition to that, these key shares, right, these random key shares, they rotate all the time. There is kind of a refresh protocol between them. So if you would want to get both key shares, right, and to be able to reconstruct the full key, you actually have to be very specific about the timing of when you do that. You essentially have to compromise both sides pretty much simultaneously in order to be able to steal any key material. Now let's talk about the security model. Again, if you can't get to both machines in one refresh period, nothing can be learned about the key material. Now, this is a pretty strong guarantee of security. And it's important to mention, this is a clear security model in the sense that you have a full proof of security, a mathematical proof of security for this assertion. It's not something that, someone said that it can be proven mathematically. Now, and here is the point that needs to be highlighted, right? The level of security that you gain is depending on the level of separation that you have between these nodes, right? So if you have these nodes, let's say on the same computer, right, it doesn't really make a lot of sense. It doesn't really provide a high level of separation. So there is a whole notion of best practices you should use in order to make sure that the deployment is sufficiently separated and secure. Okay, here are some of the methods that our customers are using. So essentially the ability to use different administrator or different credentials for different nodes, having a different operating systems or different software stacks, and obviously different environments, right? So you can imagine that you have one node on premise, other node on the cloud. You can have two nodes between two different cloud service providers. The system, essentially, the system will function exactly the same, but it will be very much segregated, right? So you can imagine different geographic locations. So that can give you a lot of combinations for a deployment that will be very, very secure. But again, it depends on the level of separation. It's very, very clear. And then, that's one of the things you need to know about when deploying such kind of a solution. And obviously, we can't continue without talking about certification. So it's important, this is the questions that we get a lot. So all the cryptography here is standard, right? So MPC essentially is a different way to compute the cryptography, but what's being computed is the same good old algorithms that we know. So RSA, ECC, AES, okay? We're just using the standard certified cryptography, but just computing it in a different way to enable MPC. So FIPS certification can be obtained, was obtained for one of our products, right? So level 1, level 2 certification. Essentially, today it's the only general pure software level 2 certified solution for FIPS 140-2. So kind of what, we discussed about few solution earlier, and what we believe about MPC, it's kind of breaking the traditional trade-off that we know, the trade-off of, software versus hardware. Hardware is secure, but, very costly and very difficult to deploy, bad usability, and software is exactly the opposite, right? So multi-party computation allows you to realize, a kind of a new solution, changing this equation, this paradigm, enabling the best of both worlds, right? So that's kind of a way to view that. We have a more kind of detailed comparison here. I won't go through all of that. Just saying that, obviously no method is perfect, right? But and you could argue that MPC has a lot of potential to help in many areas where you have challenges to protect keys today. Another interesting point here is about the need to secure the usage of the keys, not only the confidentiality of the keys that you protect, but also to properly authenticate to the keys. So that's an area where MPC can provide an additional significant value, and we will get into that in one of the examples. So let's talk a bit about applications, right? And this is all based on, real-life production scenarios of some of our customers, of course, anonymously. So I think one of the most important aspects of it is the ability to bring elasticity and automation to the world of key management. Okay, so essentially being able to be completely hardware independent. Okay, deploy in the cloud, deploy on premise, deploy in a hybrid model without being worried whether the cloud provider supports that, they don't support that, etc. Different delivery models, so it can be delivered in a VM, in a container, again, pure software, right? So scaling up and down is no issue anymore. It can be done instantaneously. And of course, easy updates, easy to deliver updates, which is, in this area, it's kind of not only usability, but also a security functionality, as we discussed when addressing vulnerabilities. And APIs, of course, so all the standard APIs, so PKCS11 based, KMIP, but also REST API for new applications. And to talk a bit about the deployment model, okay, so here I'm talking about our virtual HSM and key management solutions. So essentially it's being deployed as a set of pairs, right? So you could have these pairs in different locations, private cloud, public cloud, and connect them in a cluster, right? Seamlessly synchronizing all the keys, can be deployed globally, can be used for high availability, load balancing, etc. It's all managed within the cluster, right? So all notion of creating a high availability architecture, automatic key synchronizations, all of these issues become a lot simpler when talking about scalable and global deployments, and this is where how many of our deployments look like, essentially. This is an example of a nice example of a use case that we see pretty often about using the virtual HSM for secure code signing, right? So code signing is a rather challenging use case in the sense that you have kind of different forces, right? The developers want it to be easy. They want it to be performed on their machines or the build servers. They don't want to change anything in their process. But when you look at the security point of view, you actually want all the certificates managed centrally with a good reason, right? You want all the keys to be properly protected. And these are kinds of notions that are very much conflicting, right? And when you imagine, large organizations, large development organizations where you have a lot of developers, a lot of platforms, this is something very, very challenging to do, right? So essentially here we're talking about the ability to have the signing keys and the certificates managed centrally in a virtual HSM, connecting to the CAs, of course, to get certificates, but most importantly, enable the developers to sign the way they want. They can sign locally, as they are doing today. They can sign centrally if they prefer to do that. And for them, it's kind of transparent, right? You have and you can connect as many clients as you want. Like, for example, our flagship deployment in this area today is serving an organization with 75,000 developers, right? And as you could imagine, this means a lot of signings and a lot of certificates, right? So that's not something that is either easy or even, some could argue feasible to do with the conventional hardware systems. And this is a kind of another example. It's coming from the blockchain space, and this is referring to a different product of ours. And before I kind of go into the details, just to share a bit context about it. So in the blockchain space, talking specifically, let's say, about cryptocurrency transactions, you have a very strong need to protect the usage of the key. Because if you want to create damage, or let's say to steal money, this is mostly where it's applied, essentially, you don't need even to compromise the private key. All you need to do is just perform one signing operation, and that's it, game over. It doesn't matter if you have $1 million or $10. One signing operation, and the money is gone. And in addition to that, you can't really roll it back, right? So when it's gone forever. So this creates a lot of security issues. Those of you that know the space probably are aware of breaches that happen every week. And here, it's not only needed to protect the confidentiality of the key, but also to protect its usage. And here, essentially, we're using MPC in a way that we split the signing key to multiple shares, not only to 2, but it could be to any arbitrary number of shares, and essentially require a group of approvers, one group or a few groups of approvers that work in a quorum in order to sign any transaction. Okay, and with this model, essentially, you could argue that unless you compromise enough machines to sign an operation that you have the sufficient quorum, no transaction can go through, no matter what you're doing, right? According to the threat model. So in this example, for example, unless you infect 2 relevant machines from the first quorum and 1 from the second quorum, you won't be able to even execute a transaction, even to do a sign operation with that key. And that's, as I told you earlier, that's an area where the traditional solution usually have hard time protecting the usage, right? It's much more difficult operation to protect rather than the confidentiality, which is where the traditional solutions actually excel. So that's kind of another example. This is where mostly used by cryptocurrency exchanges. They have large operations there today. Our customers are using it to protect $1 billion in daily movements, money movements of cryptographic assets. So that's another interesting use case. And I'd say that that's kind of sums it up, right? We can talk a lot more about MPC, but I hope you got a taste of what it can do, what it's capable of doing, and we believe that it has a lot with the future of cryptography and PKI in particular. And happy to take any questions.